Let's get started and continue with our discussion on elliptic curves over local fields. Here's the setup. We are going to be working over a local field that is complete with respect to a discrete valuation new, and we set up all that notation before, but just wanted to repeat the notation. In the back of my mind, I'm thinking about QP and all these symbols that stand for all these parts and pieces of QP, but you at some point, because I'm thinking of QP because I'm thinking of elliptic curves over Q, but at some point we might want to start thinking, or you might want to start thinking about elliptic curves over number fields, and then we're going to need, instead of QP, some p-adic completion of a number field, but some prime ideal, and then the situation is just very analogous to what you are seeing here, but the valuation is a little bit different, and so on and so forth. But essentially, all the ingredients are already there for QP. Okay, so now last time, the first step to talk about elliptic curves for local fields is to choose a good Weierstrass model. And by a good Weierstrass model, what we mean is a minimal model. So if you start with a Weierstrass model with coefficients in K, then you can always just change variables so that your coefficients are in the ring of integers, first of all. So for example, one way of doing that was, so you remember that we saw using the Riemann-Roch theorem that the changes of variables of these shapes, so if you change variables to variables x prime, y prime, via one of these changes, you're going to get a Weierstrass model. And if you have a change of variables that goes from Weierstrass to Weierstrass, is one of these. And so for example, if you have a coefficients that are not in K, not in R, then then there is some pi, some uniformizer, some power of the uniformizer in the denominator, so you want to cancel it out. So if you do, for example, one simple change like this, just change x and y by those quantities. So that's the case where all these would be gone. R and S and T are zeros, and U here I'm changing by a negative power of U instead of a positive power of U. And when you change that, then the new coefficient is a power of U times AI. So you just need to change with enough of a power of uniformizer, U being the uniformizer itself, to cancel uniformizers in the denominators, and then you would go and get a Weierstrass model that has integer coefficients. Once you have integer coefficients, you want to find a model that has the smallest possible valuation of the discriminant among those with integer coefficients. Now, any such change of variables is going to change the discriminant by a 12th power and the C4 by a 4th power. But in particular, the discriminant changes by 12 powers of elements, and therefore, if you have some power of the uniformizer in your discriminant, the best you can do is reduce it by 12 or a multiple of 12. Okay. So in any case, you can just keep changing. If you have a very high power of the uniformizer, the valuation is 1,000, then you can start subtracting powers of 12. But as long as you keep your coefficients in the ring of integers. One way to check that the coefficients are still in the ring of integers, for example, is to make sure that your C4 coefficient is also staying in the ring of integers. If the coefficients are in the ring of integers, then C4 is in the ring of integers. So that is one restriction that you have to keep in mind. All right, so again, now this is the basic change of variables, and again, it changes your C4 and your discriminant by respectively a power of 12 and a power of 4. So you can deduct units from your from the valuation of the discriminant. All right. So, and then we define a equation to be minimal if the coefficients are in the ring of integers and delta has the smallest valuation among all the possible Weierstrass models. Once the coefficients are in the ring of integers, the delta is in the ring of integers, so the valuation is a non-negative integer, and therefore there is a smallest such number among all the models. by the well-ordering principle, and therefore we can pick one with that valuation, and that is a minimal model. It's not unique, as we will see in a moment. Okay, so again, we are actually interested in elliptic curves over the rationals. Okay, so here's an example over the rationals, but then the rationals are, you can embed them, since QP is a completion of the rationals, you can embed them in QP, and then think about each of the completions and see whether it's minimal at P for each one of the completions separately. So this elliptic curve in particular has that the discriminant is power of 2 times a power of 5. Since it is for P bigger than 2, the power of P is less than 12, I cannot possibly reduce it anymore, so it's minimal for every P bigger than 2. For 2, since there is a big power of 2 here, it might be that this is not minimal at 2. But if it wasn't minimal at 2, if I subtract 12 from this, I would have to be able to subtract 12 from C4. And that is not the case. I cannot do that because C4 is already minimal with respect to 2. Any such change would bring C4 into or out of the ring of integers. So what that says is that any further change of variables would actually spoil the coefficients, and the coefficients would not be in the ring of integers anymore. Okay, so so that's a remark that I wrote here that came up in a question after I stopped the video last time, and is that the minimality is defined with respect to delta. However, the valuation of C4 is helped as an aid to check whether it is possible to reduce the evaluation of delta anymore. Okay, so so the conclusion was that 2 is also minimal, even though there is a large power of 2 in the discriminant in this case. So let me give you another example. This example of an elliptic curve. So what is the discriminant in this case? The discriminant in this case, it turns out to be minus 2 to the 12, 3 to the 12 times 11 times 941. Okay, so not knowing the C4, I imagine that maybe, well, I know that this is minimal for every prime bigger than 3, because any power of a prime bigger than 3, except for 11, 941, the valuation at P is 0. For 11, 941 is 1, so it's less than 12, so they're minimal. And for 2 and 3, possibly the equation is not minimal. So you can play with possible changes of variables, and in fact, in Magma, this can be done. So in Magma, you can use, for example, the command minimal model of E. Oops, too many parentheses here. So that would bring you to a minimal model. But in any case, it turns out that a change of variables with U, R, S, T, if you pick those to be 6, minus 72, 0, minus 216, it turns out that brings you to an equation E prime of the form y squared plus xy plus 4y equals x cubed minus x squared plus 2x plus 1, or minus 1. With primes, I'm not going to write primes, but this is a new model for it. And so this change of variables brings you to this equation. And now the discriminant of my new model is minus 11 times 941. So we see that now that is minimal at all primes. So this is an equation that is minimal at all primes. And in fact, the way I constructed this was starting from an elliptic curve with coefficients 1, 2, 3, 4, 5. Okay, so this equation is actually also an equation that is isomorphic to the one above. and it is also, the discriminant is actually the same number. Okay, so they are both minimal at all primes. So there are two different Weierstrass models for my equation that are both minimal at all primes. So the minimal model is not unique. It's just the valuation of the discriminant, the smallest valuation of the discriminant is what's unique here about it. Okay, so yeah, and again, the point is that we're looking at elliptic curves that are minimal over QP. I'm not saying the elliptic curve is minimal over Q. We would say it's minimal over Q if it's minimal over all its completions, but it turns out that if you change Q by another field, that might not be possible anymore. So we always have a minimal model over a local field, because what I just said, and I'm going to write it in terms of a proposition, but this is not true over a global field. I can't always find an elliptic curve that is minimal at all primes. Okay, so here's the statement of what I just said, is that every elliptic curve E over K, where this is a local field, has minimal Weierstrass equation. Doesn't say anything about uniqueness. There is one, and again, this is not true over global fields in general. Over global fields, that equivalent statement would be an elliptic curve over a global field K, so such as a number field, where it is minimal at all primes of the number field. And that is not true, I think, in particular, when if the class number of the number field is bigger than 1, then it might not be true. Okay, B. The minimal equation is unique up to a change of variables of the form like I wrote before, u square s x prime plus t, except that if you want to go from minimal to minimal, now you can only change with a u that is a unit. And the other ones are s and t. You can pick them to be anywhere in the ring of integers, obviously. Okay. So as long as you change now by a unit, then you get another minimal model. So the two examples that I found below before, these two examples, they must differ by a change of variables with a u that is a unit. So in particular, that is a unit for all primes. So it must be either 1 or -1, the u in that case. It turns out also, let me just skip C. There's a part there about the invariant differential, so I'm just going to write D. That conversely, so what would be a converse to this is that if I go from a Weierstrass equation and get a minimal model, then the change of variables must have been with coefficients in the ring of integers. So I can't, there is no change of variables outside of the ring of integers that would go from an equation with ring of integers coefficients to an equation with a ring of integer coefficients. So this says that conversely, if one starts from a Weierstrass equation with coefficients in the ring of integers, and we apply a change of variables like before, just like this one. Let's call this change of variables this, so the same. Then, and we get a minimal model after we change of variables, then the change of variables must have been defined over the ring of integers. Okay, so that's just something technical. It's just saying you cannot go somehow. There is some weird combination of non-integers that gives you a change of variables that go from integers to integers. Okay. All right. So now what we want to do is talk about the next topic, which is the nice thing about local fields is that there is a natural reduction map to the residue field. So we're going to talk about exactly that, the reduction map. Reduction modulo pi, so modulo the maximal ideal. So so here we have, like before, we have our local field K, we have our ring of integers R, and over the ring of integers, there is the reduction map that I'm going to call twiddle down to the residue field that sends an element R to R modulo M, right? That is the natural reduction map. The natural reduction map that, for example, sends the integer, the p-adic integers are sent to FP via that map, which is isomorphic to ZP modulo PZP. Okay. And what we're going to do is now, if we have an elliptic curve E with coefficients a1xy plus a3y equals x cubed, we are going to, and I'm going to assume that it's given by a minimal model. From now on, I'm always going to assume that if I'm talking over an elliptic curve over a local field, that I have my curve in minimal form, then I can extend this twiddle to get to a curve E that is now defined by y squared plus a1, the reduction of a1 xy plus the reduction of a3 y equals x cubed plus ... And that's now a curve defined over the residue field K. Okay, I'm saying curve because this curve may not be smooth, and it may not be an elliptic curve, and that's the whole point of it. In the map sends a point here to its reduction, but the important part here is that well, if it was some x naught y naught, then it just goes to x naught y naught. However, these x naught y naught, now these are points on defined over K, and the reduction map is only defined over the ring of integers. How do we define the map in general is you have to be careful and work on projective coordinates. So the actual definition of the map sends any point can be written, so any point on EK, if P is on EK, then I can always write P as x naught, y naught, z naught, and with coefficients in R. Because if they were in K, I can multiply through by whatever power of pi I need, which is going to give me the same projective point, and eliminate denominators. Okay, and land in the ring of integers. So I can pick x naught, y naught, and z naught in R, and then send it to the reduction. Okay. Moreover, so now this may be also problematic if they're all reduced to 0. That's not a projective point. So what I can actually choose is a point with at least one of them being 0, right? If you take whatever the minimal valuation is of whatever the minimal valuation is, you can divide by that valuation, and then one of them is going to be now of valuation 0. Okay, so this map is going to be well defined as long as I pick my points in this form. Okay, then I can send them over. Let me give you an example of what I mean for this reduction map. So let's start with E is going to be the elliptic curve y squared equals x cubed minus 2. And this elliptic curve has the discriminant is minus 728, a very important number in the theory of elliptic curves. This discriminant is, so this is minus 12 cubed, so it is minus 2 to the 6 times 3 cubed. Every valuation is less than 12, so the elliptic curve is actually minimal for all p. Okay, so I can pick any prime I want. So let's pick B5 and consider now the map, the reduction map. By the way, at p equals 5, delta is minus 1728, so it's minus 3, so it's 2 mod 5, which is non-zero, and therefore the reduction, if I consider f E over f5, this is a smooth, so it is an elliptic curve. Great. In any case, my map, the reduction map that I'm interested in, goes from E to E twiddle, and it sends points x naught, y naught, z naught to the reduction mod 5. Okay, so for example, there is a point on this elliptic curve. Can you find any rational points on E? Any points on this elliptic curve over Q? So for example, so it turns out that, well, 3 cubed is 27, minus 2 is 25, which is a square, so that's a point. So P, which is 3, 5, maps to, simply I reduce the coordinates modulo 5, so it must be reduced to 3, 0 as a point on the elliptic curve f5. Does it work? Yes, because 3 cubed is 27, minus 2 is 25, which is 0. So y equals 0 is a y coordinate for that. So that's a point over f5. Great. How about if I pick, what's 2p? So if you do the addition on E, it turns out that 2p is 129 over 100, comma, minus 383 over 1,000. And now if I try to reduce it, I run into problems because, well, I have 5s in the denominator. So I can't just reduce in these two coordinates, but I can write it in in projective coordinates. So this is, if I multiply through by 1,000, I get 1290 minus 383 and 1,000. This is still 2p in projective coordinates. And now I can reduce that because not all of them are divisible by 5. So this maps to 0, 1, 0 over f5, which is O. Okay, so it turns out that that point maps to the point at infinity. What this means is that P is actually a point of order 2. It's a non-trivial, because 3 to 0 is not the point at infinity, is a non-trivial point of order 2 in the reduction mod 5. However, we will see that the order of P is infinite on E. Okay, so well, this needs to happen. If you have a point of infinite order, we know that there's only finitely many points over f5 for this elliptic curve. So it cannot be that you have point of infinite order. So they have to map somewhere. And it turns out this point, which is of infinite order over Q, has order 2 over f5. Okay. So that's, I think that's interesting. All right. So, great. So now again, in general, we're going to have an elliptic curve over K, a minimal form, and a reduction map to a curve over K. So, and then the warning here, that's actually the right warning. So delta is non-zero in K, but delta may be congruent to 0 modulo M, and therefore E twiddle may be singular. Okay, so we have to be careful with that. For example, well, I don't know, if you have delta, it turns out to be 7, and you are thinking about it as an element of Q7, then delta is 0 modulo the maximal ideal of Q7. Okay, so if you have an elliptic curve with delta equals 7, then that would be singular when you reduce modulo 7. All right, so we define then, we're going to define some subgroups according to the reduction of its points, some subgroups of E of K. So first of all, I'm going to define the non-singular points on my elliptic curve over the residue field. So this is the non-singular points on E. And remember, so recall that we've seen that actually that they form a group, that that the non-singular points of an elliptic curve, they're actually either isomorphic over K bar, they're either isomorphic to this or that. Okay, so which is the non-zero elements of K bar. Okay, depending on the reduction type, you might get that the non-singular points themselves form another group instead of the group that you have when you have the full elliptic curve when it's non-singular. Then at the level of points over K, we're also going to define two other groups, which is first of all the points on K that reduce to non-singular points. So these are the points of non-singular reduction. And E1 of K is going to be the points that reduce to 0. over the point over the finite field, over the residue field. This is the kernel of reduction. Notice that the reduction map is well, we're going to prove that these are actually subgroups of E of k. Okay, and the key is that this reduction map is going to be a homomorphism. All right, so let's actually prove exactly that. So here is the result. It is the following: that there is an exact sequence of abelian groups that goes from E naught k by the reduction map. We land on the non-singular points, and it turns out that this map is surjective and a group homomorphism. And on the other hand, E1k is the kernel of that map. So this is exactly on this side. Okay, so let's prove this. So on the groups, which are the elliptic curve and the non-singular points, remember that addition is defined geometrically by intersections of lines with the curve in P2. Since the reduction map over P2, so you can extend that reduction map to a map from P2 to P2, takes lines to lines. It just simply reduces the coefficients of the line and it sends it to another line. Let me put this camera here. Then, E naught of k is a group, and E naught k to ENS k little is a hom. Okay, so because certainly it takes lines to lines, and the addition on points in over k and addition of points in the residue field, that addition is going to be working exactly the same way because the lines are sent to lines, and the addition is just going to work the same way in both groups. Since E naught maps to it's exactly the points that map to non-singular reduction, that is going to be a homomorphism, and E1k is its kernel. So it is another group, okay, another abelian group. So all that that says is that then this is hom and this is the kernel. So that proves that part of the exactness. And the other part of the exactness that we need is that that map is surjective. Okay, so so what we need now, we need to show that the reduction map is surjective. Okay, so how are we going to do that? We're going to use Hansel's lemma. So let me go to the next page and prove that the map to the non-singular reduction is surjective. and we're going to use Hensel's lemma to build a pre-image of a point. Okay, so let E is going to be given by a Weierstrass equation, f of xy equals 0. Okay, and this is a minimal Weierstrass equation. And the reduction is just going to be given by the same equation, but with coefficients reduced modulo maximal ideal. And suppose that I have a point alpha beta, which is non-singular in the reduction. By the way, remember that the point at infinity in a Weierstrass equation is always non-singular. So the points that are singular, that are actually they live somewhere in the affine plane, and that allows me, for example, to define E1K that 0 has to be in the image. That 0 is in the non-singular reduction. Okay. Okay. So now what we need to use, just follow your nose. What do we have? We have that P is in the non-singular reduction, so it is non-singular. Since P is non-singular, or E is non-singular at P, then the formal derivatives of f with respect to x, that's terrible writing right there, the formal derivative with respect to x evaluated at P twiddle is non-zero, or the formal derivative the other way, right, delta, the other derivative at P must be non-zero. Okay, one or the other. Let's assume that the first is true. Okay, so assume that that is true. Okay, so assume that that is the one that is non-zero, and now let y not be just any lift of beta, be a point in R, or a coordinate in R with its reduction being beta modulo m. Okay. Then what happens? Then consider P of x, which is just f of x, y naught. So consider the roots of P of x. So P of x has a root alpha modulo m, right? Because P of alpha y naught is congruent to P alpha beta, and we know that it's a point on E twiddle, so this has to be 0 modulo m, right? And the other thing that we know is that P prime evaluated at alpha is non-zero modulo m because of this. Right? That is exactly what that derivative not vanishing means. And that is exactly the setup of Hensel's lemma. If you have a polynomial that has a root modulo m and the derivative is non-zero, then there is a lift. So that is where Hensel comes to rescue. So Hensel tells you that there is an x naught in R such that x naught is congruent to alpha modulo m, and P of x naught equals 0 in R. And remember that we stated Hensel's lemma a while ago when we started with some local fields work, And Hensel's lemma tells you exactly how to construct X naught in a recursive way using what's basically Newton's method to find solutions of equations, of algebraic equations. Okay, so what this translates to is that P was f of x, comma, y0, so f x naught, y naught is 0 in R now, and therefore, and thus the point x naught, y naught on EK maps to the point P twiddle alpha beta in the non-singular reduction, which is what I wanted. I wanted a lift. I wanted to show you that if I have a point, then I have a preimage of that point. So that tells you that, no, okay, sure, flatten it. That says that the map twiddle is surjective, and we've concluded the proof of the exactness of that sequence. Okay, so so what we've proved is that in general, what we can say is that E naught K maps to E and S K0, and then we have the points that map to O injecting there. Okay, so I have that exactness, but note, as long as the discriminant is non-zero modulo M, then E twiddle is all of E twiddle, or E twiddle NS is all of E twiddle, meaning that everything is non-singular. So if the delta of E is, oops, wrong symbol, is non-zero modulo the maximal ideal, then E twiddle is all of the non-singular points are everywhere, so there's no singular points. So E twiddle is non-singular. It's an elliptic curve, and therefore every point maps to a non-singular point. So you get all of E, and this tells you that then you have the points over the local field map down to the points over the residue field surjectively, and you do have the points that map to O injecting there. That's the kernel. Okay, so you do get an exact sequence just like that. Very good. So now we are finally going to bring in the formal groups. Remember that we were hoping to bring in formal groups. So one of these groups here must be the one that is the group associated to a formal group. Okay, and it's going to be U1. All right. So here is a proposition that connects now the two worlds. Oof, what the heck? Proposition. Let EK be given by a minimal value stress equation value stress equation, and let E R be the formal group associated to E, and let WZ be the power series of chapter 4. Okay, the beginning, very beginning of chapter 4. Then the map that goes from the group associated to our formal group, we're going to call it, not very imaginatively, F, to E1 that sends an element of the maximal ideal to Z WZ minus 1 over WZ is an isomorphism. And here the only question is where O goes, or where 0 goes, and 0 goes to O. Okay, so we have that isomorphism. So the formal group is going to be the piece on the left. Recall that we were looking for this. Recall that for the additive group, we always have a sequence like that. We said, yes, there is always M is inside R, and the quotient is the residue field. Great. Over the multiplicative group, what happened? Over the multiplicative group, we had units. We had the units that are 1 modulo M, and then the quotient is the non-zero elements of the residue field. Okay, meaning that the classes of units that are left, there is 1 for each other class modulo M, basically. And then we questioned that what happened with the formal group. We thought that okay, maybe there is something like this, that EK, that this formal group should fit here. Okay, so this is what we're going to prove, except that this is not always true. So this is going to be true if E is smooth. Okay, so that's what we are going to prove right now by simply proving that that this and this are isomorphic, that E1 of K and E hat of M are isomorphic. All right, so let's prove that. Proof. So this is the proof that E1K is isomorphic to E hat M. And we have a nice map. Okay, so remember that from the definition of W, the point ZWZ minus 1 WZ is a point on E over power series. Okay, so that's what we meant when we said that it was a formal solution. It's on E, and we need to check that this actually converges. So when and W was something like Z cubed times 1 plus ... It was a power series in R, which starts, well, the coefficients are in R, and it's a power series in Z. So it converges for any Z in the maximal ideal. And therefore, what that tells me is that F, remember our F is actually the map from E hat to E1, such that F of Z is that point ZWZ minus 1 over WZ. F of Z is indeed a point in EK for any Z in the maximal ideal. And what we need to check is that it's actually in E1K. It's a point that reduces to the origin. But f of z in projective coordinates, it's the point z minus 1 wz, which upon reduction, it definitely goes to reduction modulo m, right? This is reduce modulo m, it definitely goes to 0, minus 1, and wz, look, it starts, the constant term is 0. It's in fact z cubed. It starts with z cubed, so this is also 0. So this is the point 0, 1, 0, and that tells you that f of z is in fact in E1K. So the map is well defined, that it sends a point z to a point in E1K. Moreover, addition on E hat plus, on E hat, so our addition there was defined to match addition on E. Okay, so it was exactly the addition that corresponded to the addition of Z values on E. So the map is a group homomorphism. All right, so we have a group homomorphism from E hat to E1. And now I want to prove that this is an isomorphism. All right, so I have now what I know is that the map from E hat to E1 given by Z goes to ZW minus 1W is a group hom. It is injective. It is a group hom, so I just need to know what is the kernel. Well, if something reduces to 0, then it must be that Z is 0. So the kernel of F is just O. So it is injective. And now I just need to check that the map is surjective. So how about surjective? I need to pick an element in the target. So let's call this point x, y on E1. And such that, well, it's in E1, so x, y, 1 must map to, under reduction, it must map to O. Okay. So in particular, these are points, the x and y are in K, but if they map to O, there something has to be in the denominator so that when I clear denominators, I go to O. Okay. So what this tells me is that there is some alpha in the maximal ideal that clears denominators minimally, so one of them has valuation 0, such that alpha x, alpha y, alpha is 0, 1, 0. Okay. But you see that then the valuation of alpha x necessarily has to be bigger than the valuation of alpha y. The valuation of alpha y is 0. Okay, but so the valuation of alpha x has to be bigger than the valuation of alpha y. And that tells me that actually the valuation of, remember that this is, the valuation of alpha x is going to be the valuation of alpha plus valuation of x. So this says that this is the valuation of x is bigger than the valuation of y. Okay, and that tells me that then the valuation of x minus the valuation of y is bigger than 0, and that tells me that the valuation of x over y is bigger than 0. Okay, but this tells me then that x over y is in the maximal ideal, but there is an inverse map to go from points to points in the formal group. Remember that is the map, the inverse map. The way you get the z value is from a point xy, I send it to minus x over y. Okay, so then this map is the map that corresponds to the z value to that point, and what we've shown above, and above shows, let's call this G, that G, that if xy is in E1K, then G of xy is in E hat M, namely that this is an element of the maximal ideal. Okay, so with that z will map to E1K. Okay, so this is also homomorphism, and it is also injective. So this is also a homomorphism, again, by the same reason as above, because again, the z addition on z values was defined to be the addition on k on E, which is in this case the same as the addition in E1, and it is injective. So G is these things. It is also injective because if it's a hom, if xy one x if xy maps to O, then I can actually write my point as x1z. Okay, if this is going to map to this is just going to map through G to minus x, and if this is 0, then x is 0, and therefore z has to be also 0. There's only one point. Well, you can if you want, you can write the Weierstrass equation here. The Weierstrass equation would be in projective coordinates zy squared plus a1x yz plus a3 y z squared equals to the dot. If you plug in that x equals 0 and y equals 1, this gives you something like z equals a6 z cubed plus a3z squared, and this implies that z has to be 0. Because if z wasn't 0, just look at the valuation of z. Z is an integer in the local field, and the valuation of z would be equal to the valuation of z squared. Therefore, the valuation of z equals twice the valuation of z, and the valuation of z has to be well, the only way that the valuation of z is in the maximal ideal, so the valuation is positive, the only positive number such that the valuation of z equals twice the valuation of z has to be infinity. So z is 0. Okay. So it is also a hom, it's injective, and what we have now is I have more pages. Did I really talk that much? Let me add a few more pages at the end. Okay, so what we've proved is that we have a map from E, from E M to E1 of K, which is F, which is an injective Halm, and a map G to E hat M, which is an injective Halm, and the composition is identity, right? Because it sends Z to ZWZ minus 1 over W, and G through G, this would send it back to Z. Okay, to minus X over Y, you see that it gives you back Z. So it is identity, and therefore the composition must be an isomorphism. So this is each one of F and G are isomorphisms. F and G is an isomorphism. And that's what we wanted to prove. Okay. All right. So I'm going to stop here for the time being, and then I'm going to start in the next video just a little bit about points of finite order on elliptic curves.